Welcome to the 8th lecture of the course Transportation Network Analysis. So, in the last class we were discussing about branch and bound algorithm, and now we have come towards the end of that discussion. So, just take a look at a few considerations here. This branch and bound algorithm depends on efficient estimation of the lower and upper bounds of the regions or branches of the search space. Okay. So, what does that mean? So, in the worst case scenario, if no bounds are available, this algorithm will degenerate to exhaustive search. So, it can happen in the worst case scenario that we may have to evaluate all the feasible solutions of the given problem, because we are not able to find any bounds due to which we are able to prune some of the nodes or regions of this problem, and in that case we will end up doing this exhaustive search of the feasible space. And as we have discussed this before, this may not be very computationally efficient, and in many cases the size of the feasible region or the number of feasible solutions in the feasible region increases exponentially with the size of the problem. So, this is what this sentence is saying, that branch and bound finds optimal solutions, but in the worst case it may involve exploring all possible permutations and thus may not be efficient. So, until now we have not discussed about what does efficiency mean here, like what does formally we mean by an efficient algorithm. So, we will discuss about this very soon, but the final thing we would like to highlight for this branch and bound algorithm is that this algorithm, even though in the worst case it may end up being an exhaustive search, it works well in practice. Okay, so for most of the example problems, this algorithm will be able to determine the optimal solution in a reasonable amount of time. So now we come towards the end of this algorithm. So this branch and bound algorithm is guaranteed to give optimal solution, and it's very unique in the sense that we are getting the solution of an integer program by successfully solving various linear programs and trying to prune some of the branches or regions of this feasible space by getting some bounds and so on. Okay, so now let us move towards analysis of algorithms. So why that is important? Because until now we have not discussed about what do we mean by efficient algorithms. So let us go in that direction. So we'll now characterize efficiency of an algorithm here. Now the first question that is why do we care about efficiency? One answer to that is our computers are fast, but they are not infinitely fast. Okay. Similarly, nowadays we have a lot of equipments available to us that have a lot of space for storage available in them, but there is no equipment that will have infinite space and so on. So when these considerations are there, so we need to care about efficiency of algorithms. Note that different algorithms that are devised to solve the same problem often differ dramatically in their efficiency. And these differences between algorithms can be more significant than the differences due to hardware and software. Okay, so what this statement is saying, that it is important to focus on what computational time different algorithms take, and sometimes the difference between two algorithms to solve the same problem can be so much that it does not matter that which hardware or software you use, because these differences will eventually turn out very significant and they will supersede all the other issues when the problem size becomes very large. So we will soon take an example to understand what does this mean here. So let us consider this situation here. We have first this algorithm 1. So this algorithm 1 roughly takes C1 n square operations, okay, to solve a problem where C1 is a positive constant and n is the number of inputs that are required in the problem. So n, for example, can be the size of an array if you have to sort a given array, or it can be the number of nodes if you are solving the shortest path problem and so on. So n is a parameter that is defining the size of the problem. Okay. Now let us suppose that we have another algorithm, algorithm 2, that roughly takes C2 n log n operations to solve the same problem, where C2 is a positive constant. And let us assume that the base of log n is 2 here, although this does not matter even if it was another base, this example will still be relevant. Okay. So, we have now these two algorithms here, we are trying to solve the same problem, but they take different number of operations with respect to the size of the problem, and that size of the problem is characterized by this parameter n. Okay. Now, let us suppose that C1 is less than C2. Okay. For example, C1 is say 2 and C2 is equal to 50. Also suppose that it is known for small n, algorithm 1 runs faster as compared to algorithm 2. Okay. But once the input size n will become very large, the advantage of log n versus n for algorithm 2 will be more than compensating the difference in the constants. So, what does this mean here? So, the first algorithm takes C1 n square operations and the other algorithm takes C2 n log n operations. Okay. So, the difference between the expressions for the two computational times here for the two algorithms is that n is common, but for the first algorithm there is n versus log n for the second algorithm. Okay. Now, if you would have studied how does log n as n grows, so you will see that log n grows like this. So, suppose on the x axis we have n here and this is the log function. Okay. So, the log function grows like this. So, this grows at a slower rate as compared to say the function n here. Okay. So, this is the function log n and this is the line which is saying that y is equal to n here. So, log n grows in a slower pace as compared to the function n here. So, therefore, the function n log n will grow at a slower rate as compared to n square. Okay. But what we are trying to do here is that we are trying to emphasize that even if, for example, the first algorithm that takes C1 n square operations, suppose it has a very small constant. So, that is why we took C1 equal to 2, and suppose the second algorithm has C2 equal to 50 here. So, even if we provide this initial advantage to the first algorithm by giving very small constant, so that it takes very less computational time or the number of operations is very less, but this difference will eventually be in such a way that the second algorithm will become computationally more efficient as compared to the first algorithm, even though C1 is less than C2. Okay. So, there will be some n at which point C1 n square will become greater than C2 n log n. Okay. Regardless of what constant C1, C2 you choose. Okay. There will be always such an n here, because this function n log n grows as at a slower rate as compared to the function n square. Okay. To give you an example, for example, when n is equal to 1000, log n is approximately 10 when the base of this function is 2 here. Okay. So, you can see that n is like almost 100 times greater than log n when n is 1000. Okay. So, this is saying the same thing, that no matter how much smaller the constant C1 is with respect to C2, there will always be a crossover point beyond which algorithm 2 is faster. That is, C1 n square will become greater than C2 n log n at some n, regardless of how small this C1 is with respect to C2. Okay. And this will hold even if we run algorithm 1 on a faster computer as compared to algorithm 2. So, now let us try to provide another advantage to this algorithm 1 by running it on a faster computer as compared to algorithm 2. But we will see that even that advantage will be lost for algorithm 1, because again there will be some n at which algorithm 2 will become faster than algorithm 1. Okay. So, this is kind of emphasizing the fact that regardless of the values of these constants C1, C2, and regardless of what is the hardware difference in terms of running these two algorithms, the function C1 n square will eventually become larger than C2 n log n. Okay. So, let us consider an example here where the input size n is equal to 10 million. Suppose computer A executes 10 billion operations per second and computer B executes 10 billion operations per second. So, you can see that computer A is 1000 times faster than computer B. Okay. So, we will use this computer A to implement algorithm 1 and we will use computer B to implement algorithm 2. Okay. Now, let us see if we have to solve a problem that has n equal to 10 million and we are solving this problem first by algorithm 1, and this algorithm 1 is being run on a computer A that can run 10 billion operations per second. So, let us see how much time it will take to solve this problem. So, in order to calculate that, we have this 2n square where n is 10 to the power 7 because 10 million is 10 to the power 7 divided by 10 to the power 10. So, this is the number of operations that the computer A can solve in 1 second. So, this is the amount of time that it will take to run algorithm 1 here on computer A. Similarly, keeping n to be the same here, now let us determine how much time this algorithm 2 will take if it is run on computer B. So, in order to determine that, we have C2 n log n where C2 is 50 here, n log n we calculate by putting n to be equal to 10 to the power 7 divided by, since computer B takes 10 million operations per second, so it is getting divided by 10 to the power 7. So, this is approximately taking around 1163 seconds. So, you can see that algorithm 2 is taking much less time as compared to algorithm 1, even though we had given an initial advantage to algorithm 1 by giving a smaller constant 2 here as compared to 50 here, and we also ran this algorithm 1 on a faster computer as compared to this algorithm 2. Okay, so thus even with faster computer and smaller constant factor C1, it takes more time to run algorithm 1 as compared to algorithm 2 when n becomes very large. Okay. Therefore, it is important to focus on analysis of algorithms as the size of problem increases. So, we can get an idea by now that what is the target here. We want to focus on solving the problem for large n values, that is when the problem size is very large, because that is when the challenge comes. Okay. So, that is why we are focusing on the case when the size of the problem increases, that is when n is very large and so on. Because for smaller n, there might be a lot of choices in terms of which algorithm you can choose, because a lot of algorithms might be solving that problem in practical time, but you may not have that many options when n or the problem size is very large. So, we also need a model of the implementation technology here that we will be using. So, we will be using this random access machine model, which is called RAM model. So, here instructions are executed one after the other with no concurrent operations. Okay. So, it is saying that on this model all the operations will be run one after the other only. Now, there are models where you can have parallel processing also. So, there might be multiple operations that may be run parallelly, but while analyzing these algorithms we will be assuming that we have this RAM model or random access model where the operations will only be implemented sequentially one after the other, okay, and they will not be implemented concurrently or simultaneously. Okay. And one more thing is that in this random access model or RAM model, all the commonly used operations take a constant amount of time. Commonly used operations are, for example, addition, subtraction, multiplication, division, remainder, floor, ceiling, movement of data, for example, storing, copying and so on. Okay, so with this assumption it will be easier to determine how much time an algorithm takes, okay, because in a particular algorithm there might be a lot of different operations, and in order to get an idea of how much total time it takes to run a particular algorithm, we will be using this basis here. Okay, now the running time of an algorithm on a particular input is the number of primitive operations executed. Input means that the example problem that you want to solve using this algorithm and the number of primitive operations executed. So, here primitive means these kind of operations like addition, subtraction, multiplication and so on that have been mentioned above. Okay. One more very important thing is that we will focus on the worst case running time here, that is the longest running time for any input of size n. Okay. So, given problem that has size n, we want to come up with an expression for the number of operations it takes to run that algorithm in the worst case scenario. Okay. For example, if n is the number of nodes in a graph and an algorithm involves traversing all the nodes at most once, then the worst case running time is at most Cn, where C is a constant. Okay. So, in this problem, we are looking at a situation where the algorithm might traverse all the nodes at most once. So, therefore, the worst case will involve traversing all of the nodes, okay, once. So, in that case, the running time will be Cn, where C is a constant. Okay. So, C is the amount of time it takes to go to one node here. Now, there are multiple advantages for focusing on worst case running time. One is that worst case running time of an algorithm gives us an upper bound on the running time for an input. Okay. So, since we get an upper bound on the running time for an input, so then we have an idea that the running time will never exceed that situation. So, then we will be prepared for that. And another reason is that worst case in many cases might occur fairly often. For example, in searching a database for a particular piece of information, the searching algorithm's worst case will often happen when that piece is not present. Okay. So, in this situation, suppose you have to search a particular piece of information in a database. Now, if somehow we kind of know that this information is most of the time not present, so in most other cases we will have to traverse through all the pieces or all the information that are available in this database, and then we will be knowing that this piece of information is not available. So, if the number of elements of this database is suppose n, so the time it will take in the worst case situation will be some constant times n here. So, that is why this worst case will be very important in that situation. And now you can try to also think that one is this situation where we try to determine the worst case running time. There can be another alternative here. For example, rather than trying to determine the worst case running time, someone might also think of determining the average running time. Okay. So, in the average running time case, we might be interested in determining the average time it takes to run an input of size n, but doing that may not be easy, because in order to determine the expression for that, we need to have some idea of, for example, in this case when we are searching a particular piece of information in the database, we need to have an idea of what is the kind of probability of finding this piece of information and what is on an average the location of this piece of information in the database. For example, if it occurs more often at the end of this database, then the average running time will be different as compared to if it occurs more often in the beginning of the database. Okay. So, unless we have these kind of informations and so on, determining the average running time may not be very easy, and therefore we focus on the worst case running time. So, this is the point that is summarizing that thing, that in the many cases worst case running time is easy to analyze, as in the above example where a particular piece of information is not available in the database. Okay. So, in this case we were able to easily determine the expression for the worst case running time, because that will be equal to constant times the number of elements in this database. Okay. But as I mentioned, that determining the average case running time will not be that easy. So, these are the reasons we will be focusing on the worst case running time in this discussion here. Okay. So, now let us focus on order of growth. So, as I mentioned, we are interested in determining the running time as the size of the problem increases. Okay. So, the worst case running time of an algorithm for a problem is an square plus bn plus c, where n is an positive integer and that is representing the input size, and a, b and c. Suppose that the worst case running time of an algorithm for a problem is an square plus bn plus c, where n is the input size and a, b and c are constants where a is positive. So, as I mentioned, n can be, for example, the number of nodes in a problem if it is a graph problem, or it can be any parameter that represents the size of the problem here. So, in this situation we will be only interested in considering the leading term of the formula, that is an square. since the lower order terms are relatively insignificant for large values of n. Okay. So, this is saying that as n will increase, these two terms bn and c will not play any significant role as compared to the first term a n square. So, we can ignore these two terms bn and c here. Okay. And the other thing that is important here is that we can also ignore this constant a because this will also not matter that much as the size of the problem will increase. If you remember that example where we had compared two algorithms and one of the algorithm was having a constant C1 which was 2 and the running time for that algorithm was C1 times n square and the other one was C2 times n log n. Even though the constant C1 for the first algorithm was small, for example 2, and for the other one it was 50, we found that eventually this function C1 n square will overtake the other function C2 n log n. So, this constant will actually not matter as the size of the problem will increase. So, that is why in this whole expression here the most important thing is n square. Okay, the constant a, the other two terms bn and c, they are not that important. Okay. So, in the next class we will be continuing this discussion, we will be seeing what do we mean when we say that an algorithm has this much time, computational time as the size of the problem increases and so on. So, there we will be seeing that the expression that will be representing the computational time will only be having this term n square, and constant like a and the other terms bn and c that have lower importance. So, they will be not that important as the size of the problem increases. Okay, so with this we end this lecture. Thank you.